this seminar series. I'm Sungjinan, a professor at School of Computing, and I'm so glad to start this new seminar series at KAIST about artificial general intelligence. And yeah, I'm so excited about this series because given all the situations of like this fast-growing AI revolution and all LLM stuff, so we begin to talk about seriously about AGI, and some people talk about it's already here, and some people are like it's coming, and maybe some people even say LLM is not AGI. So when starting this seminar series, I wanted to invite the leaders of this field and then get share their works and also have some interviews so that we can get some inspiration from what they are thinking. Yeah, this seminar series, this is the first one, and the structure will be like we will have the talk of the today's speaker, and then we are going to have some Q&A session for which you guys can put your question into chat window. So I'm going to pick up questions and then we'll ask to the speaker. And then the third part of the seminar is to have some interview of today's speaker. So that is the structure. Yeah, I'm so honored to introduce today's speaker, Dr. Jim Fan. Jim, many of you already know of him through his Twitter. So he's very famous and well-known also influencer in Twitter. But not only in Twitter, he's a fantastic researcher working on this, actually leading this field of like general agents. He's currently a senior research scientist at NVIDIA, and he's mostly working on this embodied agent and Minecraft agent, generalist agent, which is very fantastic. So Jim received his BS degree, bachelor's degree at Columbia University as a summa cum laude, and also valedictorian of class 2016. And then he moved to Stanford, and then where he did his PhD under the advice of Professor Fei-Fei Li. Jim Fan, I think the research is very famous, especially if I pick just a few. About like MineDojo, which try to tackle very hard problem of Minecraft, solving Minecraft, so making that kind of generalist agent. And also recently, I'm very surprised about this Eureka agent, which can do some very complex control problem. So I'm not going to talk much about it because I guess Jim is going to introduce about it. Very exciting topic. So yeah, please welcome Jim. And yeah, Jim, yeah, welcome. And you can start your talk. Thank you.
Thank you so much, Sunjin, for the very warm intro. And it's my great honor to be kind of the inaugural speaker for the AGI seminar. I have never been to Korea myself in my life, and I really hope to come to KAIST next time in person and see all of you. So that is very high on my to-do list. Great, so let's get started. And I want to first share with you a story of two kittens. It's a story that gave me a lot of inspiration during my career. So back in 1963, two MIT scientists held an high. They did an ingenious experiment. They put two newborn kittens that have not yet seen the visual world in this device. And it's sort of like a merry-go-round. Basically, the two kittens are linked by a rigid mechanical bar. So their movements are exactly mirrored. And the active kitten on the right-hand side is able to move freely while transmitting the motion over the mechanical link. And then the passive kitten on the left can observe the exact same visual world as the other kitten, but it's confined to the basket, and it can't really move or control its own kind of movements. And then after a couple of days, the scientists test the kitten's behaviors, and they found that only the active kitten developed a healthy visual motor loop, while the passive kitten is not able to do things like navigate visual cliffs or respond properly to approaching objects. So I find this experiment fascinating because it shows the importance of having an embodied active experience in order to ground the input data and achieve higher levels of intelligence. Because the only difference between the active and passive kittens here is like this active agency. So let's put this experiment from 1963 in today's AI context, right? We actually have a very powerful passive kitten, and that is ChatGPT. And what ChatGPT does is it passively observes and rehearses the text on the internet, and it doesn't have any embodiment. And because of this, its knowledge is abstract and ungrounded. And I think this partially explains why ChatGPT hallucinates so much. It makes up things that are incompatible with our physical experiences. And I believe the future belongs to active kittens, which translates generalist agents. They are the decision makers in a constant feedback loop. They're embodied in a fully immersive world. And what's good about it is the active kittens are actually not mutually exclusive with the passive models. And in fact, I see it as a layer on top to really make the massive pre-trained knowledge from LLMs executable. So here's the million-dollar question, right? Like, are we there yet? Have we as a field achieved generalist agent? Long before ChatGPT, game playing agents were actually the previous wave of hype cycles. And this screenshot was taken in the spring of 2016. And back then I was, sitting in an undergraduate class at Columbia University, but I wasn't paying attention to the lecture. And instead, I was watching a board game tournament on my laptop. And at this very moment of the screenshot, AlphaGo just won 3 out of 5 games against Lee Sedol, right? The famous world champion of Go from Korea. And AlphaGo became the first bot ever to achieve this, right? And then in 2019, OpenAI 5 was able to defeat human champions at Dota, and then DeepMind AlphaStar dominated StarCraft. But beneath the glory, right, these games have one thing in common. They have a very narrowly defined goal, which is to beat the opponent. And the world is fixed and has very little room for open-ended exploration and creativity. And in contrast, I argue that a generalist agent should have at least the following essential properties. First, it should be able to pursue very complex, semantically rich, and open world objectives. You explain what you want in an arbitrary language, and the agent should perform the actions for you in a dynamic world. And second, world knowledge. The agent should have a large amount of pre-trained knowledge instead of knowing only a few concepts for that particular environment. And third, massively multitask. A generalist agent, as its name implies, it must be able to do more than just a few tasks. It should be ideally even infinitely multitask, as capable as human language can express. And according to these criteria, none of AlphaGo, OpenAI 5, or AlphaStar are really generalist agents. And then the question is, what does it take, right? How can we get there? So correspondingly, we need 3 main ingredients. First, the environment. I believe it needs to be open-ended enough because the agent's capability is upper bounded by the environment complexity. And here, Earth, the world we live in, is a perfect example, right? It is so open-ended that it allows an algorithm called a natural evolution to produce all the diverse forms of life that we see today. So the question is, can we have a simulator that is essentially a lo-fi Earth, but we can still run it on our lab computer? And second, we need to provide the agent with massive pre-training data, basically making the passive part of this loop, because exploration from scratch in an open-ended environment is simply intractable. And this data will serve 2 purposes. One is as a reference manual on how to do things. And second, as a guidance for what are the interesting things worth doing. And the GPTs only learn from pure text on the web, but can we take it one step further and provide the agent with much richer data, such as video walkthroughs, multimedia tutorials, and free-form wiki documents? And finally, once we have the environment and database, we're ready to train foundation models for agents. it should be flexible enough to pursue open-ended tasks without task-specific assumptions, and also scalable enough to convert the large-scale multimodal data into actionable insight. And ideally, we want language to play two key roles. One, as an intuitive interface to communicate a task by prompting, and second, as a bridge to ground the visual concepts. And this very long line of train of thought lands us in Minecraft, the best-selling video game of all time. And for those who are not familiar, Minecraft is a procedurally generated 3D voxel world. And in this game, you can basically do whatever your heart desires. And what's so special about the game, right, is that unlike AlphaGo and AlphaStar, Minecraft defines no particular score to maximize and no fixed storyline to follow. And that makes it very well suited as a truly open-ended AI playground. And as a result, we see very impressive creations. Like here, someone on YouTube built the entire Hogwarts castle block by block in Minecraft. And this is one more example. A very beautiful temple inside a deep cave that's just dug out by the player, and then with an underground river nearby. Absolutely mind-blowing structures. And here's someone who built a functioning CPU circuit within the game, because apparently Minecraft supports logical gates and is actually a Turing-complete game. Absolutely insane. And I want to highlight a number here. Minecraft has 140 million active players. And just to put that number in perspective, this is more than twice the population of UK. And it just so happens that gamers are generally happier than PhDs. So they really like to stream and share. And this huge human mass produces an enormous amount of online knowledge every day. So the question is, can we tap into this treasure trove of learning materials? Because the data is always the key ingredient to foundation models. So we introduced MindDojo, a new open framework to help the community develop generally capable agents using Minecraft as a kind of primordial soup. And MindDojo features three major parts: an open-ended environment, an internet-scale knowledge base, and a generalist agent developed with a simulator and a massive data. So let's zoom in the first part. Here's a sample gallery of the interesting things an agent can do in MindDojo. And actually, we feature a massive benchmarking suite of more than 3,000 tasks. And this is among the largest open source agent benchmark ever created to our knowledge. We implement a versatile API in MindDojo that unlocks the full potential of the game. Like, for example, it supports multimodal observation space and action space. And MindDojo can be customized at every detail, like terrains, weather, block placement, and monster spawning. And given the simulator, we introduce around 1,500 programmatic tasks, which are tasks that have ground-truth success conditions defined in Python code. You can also explicitly write down the sparse or dense reward functions using the API. And some examples of programmatic tasks are harvesting different resources, learn to master the tech tree, or combat various monsters. And all the tasks come with some kind of language prompts. And here are templates like harvest n units of a certain resource in a certain terrain. And as we mentioned, right, what is special about Minecraft is that it's freeform and open-ended. So we also introduced 1,500 creative tasks. And in contrast to programmatic tasks, creative tasks don't have well-defined or easily automated success criteria. For example, let's say we want the agent to build a house. But what makes a house, right? It's very difficult to use simple Python code to determine these creative missions. And the best way is to use a model, foundation model, trained on internet scale knowledge, so that something like the abstract concept of a house can be captured. And finally, I want to mention one task that holds a special status, and it's called playthrough, which is to beat the final boss of Minecraft, the Ender Dragon. So Minecraft doesn't force you to do this mission, but it is considered a big milestone achievement for any beginner player. And I want to highlight that this is an extremely difficult task that requires very complex preparation, exploration, planning, and of course, fighting skills. And for an average human, it takes many hours or even days to solve, easily over 1 million action steps in a single episode. And I believe that would be the longest horizon ever in a decision-making benchmark. And here I admit, I myself am a below average human. I was never able to beat the Ender Dragon, so I really want my AI to avenge my poor skills someday. Now, let's move on to our second ingredient, the internet skill knowledge base of MindDojo. We offer 3 databases, YouTube, Wiki, and Reddit. And combined, they are the largest open-ended agent database ever compiled. And the first is YouTube. We find that Minecraft is among the most streamed games on YouTube, and gamers just love to narrate what they're doing. So we collected more than 700,000 videos with 2 billion words in transcript. And these transcripts help the agent learn about human strategies and creativity without us manually labeling everything. Second, players have compiled a large Minecraft-specific Wikipedia that explains everything you ever need to know in the game. And we scrape 7,000 wiki pages with interleaving multimodal data like images, tables, and diagrams. And here are some examples. This is a gallery of all the monsters and their spawning or attack mechanisms, all explained on Wiki. And also the thousands of crafting recipes you can find. And the complex diagrams, tables, and embedded figures, we all scraped and compiled into the Wiki database. And finally, the Minecraft subreddit is a very active forum. Players showcase their creations and also ask questions for help. And we scrape more than 300,000 posts with 6 million comments. And here are some examples of basically people using the Minecraft subreddit as a kind of Stack Overflow for Minecraft. And we can see that some of the top voted answers are actually quite good. Like someone is asking, like, why doesn't my wheat farm grow? And the answer is, you don't have enough light. So if you add more torches, your wheat will grow. And that's actually the correct answer. So now, given the massive task suite and the internet data, we have the essential components to build generalist agents. And in the first MindDojo paper, we introduced a foundation model called MindClip. And the idea is very simple. For our YouTube database, we have time-aligned video clips and transcripts. And here on this slide, these are real tutorial videos. Like in text prompt 3, as I raise my axe in front of this pig, there's only one thing you know is going to happen. This is actually an excerpt from a real YouTube tutorial video. So we train MindClip in the same spirit as OpenAI Clip. And for those who are unfamiliar, OpenAI Clip is a contrastive model that learns the association between image and text. And here, MindClip is a video text contrastive model. And each of the video snippet during training is about 8 to 16 seconds. And we simply go through the clip training to learn encoders for the video and text. Intuitively, what MindClip learns is the association between the video and the transcript that describes the action in the video. And MindClip outputs a score between 0 and 1, where 1 means perfect description, and 0 means that the text is irrelevant to the video. So you can think of it as a language-prompted foundation reward model that understands the nuances of different terrains, animal behaviors, and architectures in Minecraft. And now let's put MindClip to action. Here is an example of our agent interacting with the simulator. The task is shear sheep to obtain wool. And as the agent explores, it generates a video snippet as a moving window, which can be encoded and fed to MindClip. And MindClip computes the score. The higher the association, the more the agent's behavior aligns with the language. And so we know that it's on the right track. And that becomes the reward function to any reinforcement learning algorithm. So this whole stack looks very familiar, right? because it's essentially reinforcement learning from human feedback, or RLHF, in Minecraft. And RLHF is the cornerstone algorithm that makes ChatGPT possible, and I believe it will play a critical role in generalist agents as well. So I'll quickly gloss over some quantitative results. For these 8 tasks, we show the percentage success rate over 200 test episodes. And here in the green circle is 2 variants of our Minecraft method, and in the orange circles are the baselines. We construct a manual dense reward function for each of the tasks using the privileged simulator state. And this column, you should consider it as an oracle result that's approaching the upper bound, because the RL algorithm is being shaped smoothly towards the goal, and we had a lot of manual engineering into each reward function. And we also have a sparse reward baseline. And then you see in the green box, agents trained with Mineclub are able to match the quality of manually engineered rewards in many tasks. And it's important to stress that Mineclub is open vocabulary, which means we did not train Mineclub specifically for the benchmark tasks. We simply prompt Mineclub with the text description of the task, and then reuse the same model for all of the tasks. And one major feature of foundation models is strong generalization out of the box. So we test out, can our agent generalize to dramatic changes in the visual appearance? So we did an experiment where during training, the agent only sees the default terrain at noon on a sunny day, but we tested zero shot in a diverse set of terrains, weathers, and day-night cycles. It's all supported by Mindojo API. And we showed in our paper that Mineclub significantly outperforms an off-the-shelf visual encoder when facing such dramatic distribution shift without retraining on any of these novel test domains. And this is not surprising, right? Because Mineclub is trained on hundreds of thousands of YouTube videos, which gives it a very good coverage of all kinds of scenarios. And that's just a big advantage of using internet scale in the wild data, because you get robustness out of the box. And here are some demos of our learned agent behavior on various tasks. And you may notice that these tasks are relatively short, between 100 to 500 steps. And that's because Mineclub was trained with only like 8 to 16 seconds of video, so it's not able to plan over very long time spans by design. So that's a limitation. But our hope is to build an agent that explores and makes new discoveries continuously without human intervention. And back in 2022, that goal seemed out of reach for us. And then something great happened in 2023, where GPT-4 came, a language model that's so good at coding and long horizon planning. So we revisited the problem and built Voyager, the first large language model powered lifelong learning agent. And here in this video, we set Voyager loose in Minecraft, and it's able to play the game for hours without intervention. And the video here is not snippets from different training episodes. It's a single episode of Voyager. Just kind of keep going. It explores the terrains, mine all kinds of materials, fight monsters, craft hundreds of recipes, and unlock an ever-expanding tree of skills, just continuously all by itself. So what's the magic behind the hood? The first question is, if we want to use the full power of GPT-4, then we need to convert things to text. So how do we convert this embodied multimodal environment into strings within the magic box? And thankfully, the enthusiastic Minecraft community already built one. It's called MindFlayer, a high-level JavaScript API that's actively maintained to work with almost every version of Minecraft. And the beauty of MindFlayer is that it has access to the game state surrounding the agent, like the nearby blocks, animals, and enemies. So we effectively have a ground truth perception module as a textual channel. And now that we convert everything to text, we're ready to construct an agent algorithm on top of GPT-4. And on a high level, there are three components. First, a coding module that writes JavaScript to control the game part. And it's the main module that generates executable actions. And second, a code base to store the correctly written code and look it up in the future if the agent needs to recall the skill. And in this way, we don't duplicate coding efforts and achieve a form of learning, but without gradient descent. And third, we need to know what to do. So we implement a curriculum that proposes what to do next, given the agent's current capabilities. And when you wire these components up together, you get a loop that drives the agent indefinitely and achieves something like lifelong learning in context. So let's zoom in the center module. We prompt GPT-4 with documentations and examples on how to use a subset of the MindFlayer API. And then GPT just writes the code to take actions given the current assigned task. And because JavaScript runs a code interpreter, GPT-4 is able to define new functions on the fly and run it interactively. But the code that GPT-4 writes isn't always able to get it right on the first try. So we develop an iterative prompting mechanism to refine the program. There are three types of feedback. The environment feedback, like what new materials did you get after taking action? The execution error from the JavaScript interpreter, like let's say variable undefined error. And another GPT-4 that provides critique through self-reflection from the agent's own states. And these help the agent refine the program effectively. I want to show some examples of how the critic can provide feedback on the task completion progress. So in the first example, the task is to craft a spyglass. GPT-4 looks at the inventory and decides that it has enough copper, but not enough amherst. And the second task is to kill 3 sheep to collect food. And each sheep drops 1 unit of wool, but there are only 2 units in the inventory. So the critic decides that 1 more sheep needs to go. And finally, here's an example about zombie. Where you kill the zombie, it drops a unit of rotten flesh, and it's in the inventory. So GPT-4 decides that the task is successful and moves on to propose the next task. Now, moving on to the second part. Once it implements a skill correctly, we save it to a persistent storage. So you can think of the skill library as a code base that's authored purely by GPT-4 through trial and error. And then the agent can just retrieve the skill from the library when facing similar situation in the future. So it doesn't need to implement and then do the trial and error loop all over again. And in this way, Voyager improves itself as it experiments more and more in Minecraft. So let's dive a bit deeper into how the skill library is implemented. This is how we insert a new skill. First, we use GPT 3.5 to summarize the program into plain English. And summarization is very easy. Doesn't need GPT-4, so we save some money. And then the embedding of the summary becomes the key and the program becomes the value. And then we insert it into a vector database. We find it better empirically to embed the description instead of a raw program because it's more semantic and improves the retrieval. And now when Voyager is faced with a new task, let's say craft iron pickaxe, we use GPT 3.5, again, save some money, to generate a hint on how to solve the task, and then combine it with the world state as a query vector, and we embed that as a key and retrieve the top 5 relevant skills from the vector database. And here, Voyager is free to directly use one of the skills as is, or interpolate between the 5 retrieved skills, or write one from scratch completely. And in this way, we maximally reuse the old experiences while giving Voyager enough flexibility. So you can think of it as an in-context replay buffer in the RL terminology. And now moving on to the third part, the curriculum. We have yet another GD4 that proposes what tasks to do given its current capabilities. And the curriculum has an unsupervised objective, which is to maximize the number of novel items that the agent obtains. And that's all we give it. And it's able to propose a progressively harder curriculum over time. So there are two key insights here. One, this is a form of curiosity-driven exploration or novelty search in prior literature, but implemented purely in context. And two, it is a situation-aware curriculum that takes into account the agent's capability currently. So it doesn't propose a task that's either too difficult or too easy. And GD4 decides all of that without any manual prescription from us. And putting all these pieces together, we have an iterative prompting mechanism that refines the program by self-debugging, a skill library as an in-context replay buffer, and an automatic curriculum as an in-context curiosity-driven exploration. And all of these together is Voyager's no-gradient architecture, where we don't train any new model or fine-tune any new parameters. And it allows Voyager to self-bootstrap and perform lifelong learning in an open-ended world. So these are the tasks that Voyager happens to pick up along the way in a single episode. We didn't pre-program any of these. It's all Voyager's idea. The agent is forever curious and forever pursuing new adventures. And we've done a lot of study for Voyager in the paper. And here is one quantitative learning curve, where the x-axis is the number of prompting iterations, and the y-axis is the number of unique items obtained by each agent. So I'll quickly gloss over the baselines. These curves are the baselines, like React and Reflexion from prior works. And this is where Voyager is, where we can see that it's able to quickly find novel items and then do a lot of exploration and unlock the whole tech tree significantly faster, from wooden to stone to diamond tools. And the blue curve here is an ablation of Voyager without the skill library. So we can see that it learns much slower and also plateaus after a while. So it is essential for the skill library to unlock Voyager's lifelong learning abilities. And here are two bird's eye view of the Minecraft map. So these circles are what the prior methods are able to explore given the same iteration budget. And we can see that they tend to get stuck in local areas. And this is Voyager, where it's able to navigate distances 2 times longer compared to prior works. And that comes as no surprise because Voyager needs to visit more diverse terrains in order to find the novel items quickly. And because it travels a lot, and that's why we name it Voyager. And finally, I want to point out one limitation is that Voyager does not currently support visual perception because back then the GPT-4 we used, the API was text only. But there's nothing stopping Voyager from using, let's say, a multimodal model to achieve more impressive tasks. And here we demonstrate that if we swap out the critic with human, then Voyager would be able to construct complex 3D structures in Minecraft, such as a farmhouse or another portal. And the human basically look at the scene and act as the pair of eyes for Voyager and give it 3D spatial advice. And to build very complex structures, I think we need full-blown multimodal models, something either like GPT-4V or some open source models. And I'm leaving that to future works. Well, and now we've been thinking, right, after finishing Voyager, the algorithm is general purpose and does not limit to Minecraft. So we ask ourselves, where else can we apply this idea of iterative coding and refinement in an embodied environment and observe the feedback and then produce a better version of the code. And we came to realize that physics simulation are actually just Python code as well. And here's a snippet of the Allegro hand environment implemented in NVIDIA's ISAGym physics simulator API, right? And it's just code. From a Voyager point of view, it's coding and a code out. So what if we apply Voyager in the space of this physics simulator API? And this is Eureka, which my team announced last month. It is an open-ended agent that designs reward functions for robot dexterity at superhuman level. And it turns out that GPT-4 plus reinforcement learning can learn to spin a pen better than I could ever do. And I gave up on this task long ago since childhood. I was never able to spin pen very well. And the idea is very simple and intuitive. GPT-4 generates a bunch of possible reward function candidates. And then you do a full reinforcement learning training loop for each candidate on a GPU accelerated simulator, ISAGym, and you get the performance metrics, and you take the best candidate. And then GPT-4 samples the next proposals based on this best candidate and keeps improving. So what I just described is a kind of in-context evolutionary research. And I want to break down the process a bit more. Here is the initial reward generation, where Eureka takes as context the environment code of NVIDIA's ISAGym and a task description, and then samples an initial reward function candidate. So we give it the simulator code because it is a very good reference manual. It tells Eureka which variables to use, like the object angular velocity, the target pose, fingertip location, etc. And it also tells you how these variables interact with each other. It's also got some inline comments that GPT-4 can reference. And then once the reward is generated, you plug it into an RL algorithm and just train it to completion. And this step is typically extremely slow and could take days or even weeks. And we're able to scale up Eureka because ISAGym runs thousands of simulator copies in parallel on a single GPU card, basically speeding up reality by 3 orders of magnitude. And that's how we're able to make this problem tractable. And then after the training, you get the performance metrics back on each reward component. And as we saw from Voyager, GPT-4 is exceptionally good at self-reflection. So it reflects on the results and then proposes mutations on the code for the next iteration of evolution. And here I show some examples of the mutations that GPT-4 proposes. It could be very diverse, from straightforward, just changing a single hyperparameter, like a rotation reward temperature, to adding completely novel components. And it's all GPT-4's idea. And in our experiments, Eureka becomes a superhuman reward engineer, actually outperforming many of the functions implemented manually by the expert engineers on our NVIDIA ISAGym team. Writing a reward function is a very kind of manual trial and error and a very painful process. So we're glad that Eureka offers a way to completely automate this and even perform better than the domain expert, the human domain experts. So showing some more of the dexterous hand examples. And I want to highlight that a major contribution of Eureka is to bridge the gap between the high-level reasoning of LLMs and low-level motor control. So Eureka uses a new paradigm that I call hybrid gradient architecture. That's compared to the no gradient architecture from Voyager. And the hybrid gradient architecture means a black box inference-only LLM instructs a white box learnable neural network. So the outer loop is a gradient-free optimization process where it runs the GPT-4 as a black box to refine the reward function, while the inner loop is gradient-based and trains an RL robot controller to achieve extreme dexterity. And you must have both loops in order to succeed. And I think this will also become a very useful general purpose approach for embodied agents in the future. Okay, so I want to pause a little and take some questions, but I have a bit more slides about kind of looking forward, what are things that I'm most excited about next.
Right. Yeah, if there's any question, please raise your hand or ask it in the chat window. So Jim, maybe you can read the chat window. There's one question from Mino.
Oh, yep. From Mingho. Have you ever experimented with comparing the visual representations learned by an active agent with those learned by a passive agent? It will be fascinating to explore. I think that is a very interesting suggestion. So for our MindClub experiment, we froze the reward function. So MindClub is a reward function, and we reuse MindClub's visual encoder as a frozen feature extractor for the agents. So we did not kind of fine tune the gradients. So we did not backprop the gradients back all the way to the visual encoder. But this is a very interesting suggestion. Yeah, I will come. So MindClub is open source. The whole model and the weights and the code are open source. So feel free to try it out and let us know if you find some interesting things about the active kitten. Great. Any other questions? Okay. Could Minecraft trained Voyager model be adopted to other domain tasks as well as ChatGPT does? So Voyager is kind of quote unquote trained by writing the skill library, right? Like because we don't have a way to fine tune GPT-4's weights directly. So Voyager is a kind of explicit learning in the form of writing a code base. And that code base will not transfer, but Voyager itself will. So, something like Eureka is a type of self-reflection and iterative code refinement, borrowing principles from Voyager. So I think you can apply something like Voyager with a skill library to a new domain where Voyager just explores and then write things into the skill library. And after a while, it will be able to have, like I said, reusable skills. But the skills trained in Minecraft, which are code tied to Minecraft, will not directly transfer to other environments. Yeah,
Right.
Thanks for the question.
So I think because we have the allocated time for question answer, so after the talk, so maybe now we can go proceed the talk, and then after the talk we can do more questions. Would that be good?
Okay, great. Sounds good.
Yeah.
So like these days when I go on Twitter, I see AI conquering new lands almost every week, right? Now AI does chat a long time ago and image generation. And actually today, like DeepMind dropped a new work on Generalist that is really good. So it seems that generative AI is invincible. But I believe agents will be kind of the last moat that we conquer. And MindDojo and Voyager are just scratching the surface of open-ended generalist agents. And I still think there are many challenges ahead. And this is a very kind of interesting topic that I believe will need a few more years for AI to master. So looking forward, I want to share two key research directions that I find very promising. The first is a continuation of MindClub, right? How to develop methods that learn from internet skill videos. And the second is multimodal foundation models, starting from GD4V, and GD4V doesn't even support video. So I think there's a lot more work to be done on this area. So we all know that videos are abundant, right? Way too many for limited GPUs to process, and they're extremely useful. not just to train representations, but also to understand, and intuitive physics. It's all good, except that for agents, videos don't come with action labels. So there's no free lunch there, right? Like how to extract a policy from a video is a very difficult problem. And here is a demonstration of why learning from video is hard even for natural intelligence. So you see the cat is looking at a boxer, and then a boxer like Mike Tyson is shaking his head, and the cat doesn't really know why he shakes his head, so it just imitates superficially. Let's look at the video again, right? Mike Tyson is like shaking, right? And the cat learns the strategy, but doesn't understand the causality from the video. And then it tries to apply that. I don't think it helps the cat in the fighting skills, but it definitely boosts its confidence, right? So learning from video is very hard. You don't get the actions. You don't understand why certain things are being done that way because it's passive. Now, let me highlight a couple of ways to use videos. And these are just preliminary kind of explorations, and a lot needs to be done. So the first is the simplest, just learn a feature extractor from the video. And this paper R3M is from Chelsea Finn's group at Stanford, where you learn an image level representation, but using video level loss functions, like time contrastive learning or video language alignment. And then you can simply use this feature extractor and put it as a module in any robot learning task. But this one does not learn any policy. And the second path is to learn a reward function. And MindClip is one example we have already talked about. And this work VIP is another way to learn like a similarity-based reward for image goal condition task. It's led by Jason Ma, who's also the first author of Eureka, and my current intern at NVIDIA. And the third idea is very interesting, right? Can we extract a policy directly by imitation learning from video? But we just said that videos don't come with action labels. So one way is to find some clever path to pseudo-label the actions. And this is a video pre-training of VPT from OpenAI to solve long horizon Minecraft tasks. So here, VPT works by first hiring a bunch of human contractors to play Minecraft and collect about 2,000 hours of the videos and the keyboard and mouse actions that a human did. So you can train an inverse dynamics model, which takes in neighboring frames and then predict the keyboard and mouse action. And now you have a pretty good inverse dynamics model. You can use it as a pseudo labeler to label the 70,000 hours of in the wild YouTube videos. And now that becomes an augmented behavior cloning dataset. And then you simply train imitation learning on top of all of these data. And you will be able to learn a policy with this kind of pseudo annotation. So VPT is not language conditioned, but MindClip is. And I believe there are a huge synergy between these different approaches. So what is beyond video, right? I am a firm believer that multimodal foundation models will be the future. And GPT-4V is a good start, but we should have text, audio, video, and someday even 3D, all part of a giant multimodal foundation model. And here in the context of embodied agents, I think the input can be a mixture of all the modalities I mentioned, and the output can be actions. So here's one example of what a multimodal foundation model would look like for robot learning. So let's imagine a household robot. We can ask the bot to bring us a cup of tea from kitchen. But if we want to be more specific, we can instead say, oh, bring me this image of the cup, of my favorite cup. We can also provide a video demo of mopping the floor this way and ask the robot to imitate our motion. And when the robot sees an unfamiliar object like a sweeper, we can explain by an image example, like this is a sweeper, and we teach the robot a new concept in context. And finally, to ensure safety, we can point to a room and just ask the robot not to enter. And to achieve this, in ICML 2023, we propose a model called VIMA, where in this work, we introduced multimodal prompting, which can be a mixture of the text, image, and video frames as part of the instruction. And I'll quickly give some examples, like, for example, visual goal reaching can be expressed in rearrange objects to match the scene, and you provide an image of the scene, and the robot will be able to kind of rearrange and then satisfy this image goal. And you can also teach the robot new concepts in context, like explaining what is a blicket and what is a woog. Both are nonsensical words, just to kind of ground the concept. And after showing these new definitions, the model learns to use them immediately in context, condition on the command. We can ask the robot to follow a sequence of motions for a particular object, which is essentially a tiny video clip. And traditionally, this task is called one-shot video demonstration. But here it's just expressed as like a multimodal prompt. And finally, a visual constraint, sweep all the cubes into this bin without exceeding the line. And recently, Google Brain Robotics follow up after VIMA with RT1 and RT2. So RT2 is using a very similar recipe as I described, where they first pre-train a vision language backbone on internet scale data, and then fine-tune it with some kind of human collected demonstrations on the Google robots. So in principle, it is also like a multimodal mixture prompted model, very similar to VIMA. And RoboCat from DeepMind is another interesting work, where they train a single unified policy, not only on multiple tasks, but also multiple embodiments, and show generalization to new robot hardware. So yeah, that concludes our looking forward section. These two directions are what excite me the most. Happy to discuss this more offline as well. And here I will just put some links to the works I mentioned. We're big fans of open sourcing. And for all the projects I talk about, we basically open source everything, model code, weights, simulator, training data, you name it, as much as we can share. So this is the MindDojo website, minddojo.org. This is voyager.minddojo.org. This is Eureka and VIMA. And one more thing, right? If you just want an excuse to play Minecraft at Sunjun's class, MindDojo is perfect for you, right? You would just say, right, you are collecting data for science, right, to train generalist agents in MindDojo. Perfect excuse. And lastly, I want to remind all of us, right, what we can do so far with these new algorithms are impressive, but they are still very far from ingenuity that the human players have demonstrated, like decorating a winter wonderland or simulating a CPU circuit. So here's a call to action for the community. If humans can do these mind-blowing tasks, then why not our AI? So let's find out together. And all of these projects are big teamworks at NVIDIA. A big shout out to all of my amazing collaborators. And life is short. We should do hardcore AI research and have fun at the same time. And by the way, my team is hiring. So please reach out to me by email or Twitter, whatever you like. And yeah, thank you so much for attending.
Right. Yeah, thank you, Jim. This is really great talk, very thought-provoking and very exciting. Actually, yeah, I was very surprised when I first see this MindDojo thing, and then doing it like at that time I was working on like this crafter, small like miniature version of Minecraft, and it was so hard to tackle it. But after seeing this paper, I was so excited. Yeah, great. Yeah, hi everyone. Yeah, thank you for the great talk. Yeah.
Thanks for inviting me. Yeah,
and
very glad.
yeah, so I think we have some questions for the remaining part of the seminar. So we have some question session from the audience about the talk, and then we are going to go to some interview. So I think Luis asked some question about Eureka. The idea is very interesting, and he's asking, in the outer loop, you still need a reward function in dexterity environment. Can you talk a bit more about this feedback in the outer loop?
Yeah, so here the reward function is a central bridge between the LLM, the high-level reasoning, and the low-level control. So we don't provide Eureka with like human written reward at all. It's all GPT-4's idea. The only thing that we provide is like the environment code, where we show kind of this environment, this simulation is implemented this way with these variables that you can use for the reward function. That's all we give it. So basically, even for a human engineer to write a reward function, you need to read the documentation of Isaac Gym, and you to read kind of some code bases of how certain tasks are implemented. So this is very much kind of the human level input. And then GPT-4 is able to propose like better and better reward functions and it drives kind of better and better policies by itself. And for this part, you can also imagine humans do similar things. I actually interviewed some like NVIDIA Isaac Gym engineers, and they were like, we write reward functions by running it and just try it out and see if there's something weird. If there's something weird, we'll correct the reward functions. So basically, Eureka automates that whole process that the human domain experts do, and Eureka does it better.
All right. The next question from Bao. He's asking basically the limitation of GPT-4. It's very fantastic common sense knowledge, but it also has some limitations. So he's asking basically, do you think the knowledge in GPT-4 is enough to be a great Minecraft player, or to which extent should we augment the GPT-4 for better performance? And like a GPT-4 is like a compression of the knowledge, and he's also asking what is the best way to extract good knowledge from the GPT-4, like for example using prompting.
Yeah, that is a great question. So we found that GPT-4 actually knows a lot about Minecraft, probably because Minecraft is just one of the most talked about game on the internet. And it has a big subreddit. I'm pretty sure it's in the training corpus of GPT-4. So it knows a lot about the game. We actually try to give it like a wiki retrieval, but it doesn't help too much because it already knows a lot of that. And GPT-4 does hallucinate, but it's okay. Because if it hallucinates, it will execute some code that is incorrect in the environment, and it will get the feedback from the environment to correct its hallucination, right? So kind of back to the beginning, I said that the active kitten will be able to ground the abstract knowledge and reduce hallucination. And we do see that in Voyager. You can ask it questions, if you're just doing question answering, it can hallucinate. But if it actually needs to execute the action and observe the feedback, then it has less room for hallucination and also better chances to correct itself. So this kind of active embodiment is critical.
Yeah, so the next question from Umaz about like the quality of creativity of the MindDojo agent, what it can create in the game. Would it be as good as what human expert create in the environment? Is there some kind of the level of creativity? Can you compare how it can be compared to human experts' ability, or if it is not at that level, why, or that kind of question?
Yes. So it is not at that level because for MindDojo and MindClip, because of the way MindClip was trained, we are not able to do very long horizon tasks. So for example, if you want to be creative, let's say build a house, it takes probably tens of thousands of steps of action steps in the simulator to build a house. And simply MindClip is not able to handle that. So that is a limitation. And for Voyager, it's able to do longer horizon, but it doesn't see the pixels. And for many of the creative tasks, you do need to have the visual feedback to actually do something like building a house. So it's still very difficult for both MindDojo, MindClip, and Voyager. And it's like a big kind of unsolved remaining problem in Minecraft, right? How to build houses, how to build like castles, as well as those demonstrated on YouTube. So I do think there are a lot remaining to be done. And please try out MindDojo. I would love to see kind of more research enabled by this framework.
Yeah, the next question from Juyong. He's asking about the comparison between neural net policy and or parametric policy, which can be updated through gradient descent, and also the code policy, where the code is generated by LLMs. So, like in your work, Eureka. So, is there some pros of neural net parametric policy over the code policies? How can we compare that? Actually, this is very interesting. Also, what I thought in your talk, it is kind of proposing a new paradigm of machine learning. So in the past, we were talking about mostly parametric approach where learning is parameterized in the weights. But now we don't do what you said, like a no gradient framework, where somehow the knowledge is already amortized in the large language model. We just need to patch what we want through some nice. So that is kind of sounds like a new framework of machine learning, what we're doing. I mean, so I think this question is asking that aspect, comparing, especially in terms of policy.
Yeah. I think that is a great question. So I think moving forward, we will see more and more hybrid gradient architectures because no gradient and fully parametric, they have pros and cons. And I think the best way is just to combine them. So for the no gradient architecture, right, like it's able to kind of write code and do very complicated reasoning and log horizon planning that I simply don't think kind of parametric models, parametric policies is able to do very well. You should do a lot of those planning explicitly, leveraging LLM zero shot and reasoning capabilities. So that part will be no gradient. And then the part that requires gradient will be the low-level controls, where the control itself cannot even be easily expressed in language. So Voyager is able to do that because it calls APIs that does some of the low level. So we abstract away some of the low level actions. But a lot of actions are non-trivial, right? So let's say if you want to dig a hole, for example, you need to look down and then maybe click a mouse to dig the hole. So it's actually like a set of actions that are low level, but we simply call like function, dig one block, for example. This is like one primitive function that Voyager is able to call. So we abstract away that in Voyager, but the problem doesn't go away. Like if we want to translate to something like robot actions, we will need a parametric policy to do like dexterous control, because the dexterous control cannot be expressed by language. And once you're able to do that, kind of the higher level compositional part can be done by LLMs in a kind of prompting or like skill library or these no gradient architectures. And I think we need this bi-level setting of a hybrid gradient architecture moving forward. So that is my best guess. And I feel that, in the kind of the current age of like foundation models, especially good coding models, the neurosymbolic AI is making a comeback. And we can finally do truly functional neurosymbolic AI. Like before foundation models, they don't really work, but now they do, because we have LLMs that have these kind of amazing abilities to generate symbols and manipulate symbols and compose symbols. And then the symbols can work with parametric models that control all the way down to the torque of your finger. So neurosymbolic AI is coming back.
Yeah, actually, yeah, that's very interesting point. Like, yeah, right, the return of neurosymbolic AI through this like language interface and with the
Exactly.
yeah, that's very interesting observation. Yeah, right. Yeah.
Great
The
question.
next question is Dongjin. When defining actions, it is possible to define them using API code generated by an LLM like Voyager, or through keyboard and mouse action. In the later case, a foundation model be used for high-level planning, while a low-level policy would be run via RL? Which of these two approaches do
I
you
think
think? Yeah. Mhm.
it's the same as the discussion we just had about hybrid gradient.
Mhm.
So I think
Mhm.
what the students just hear is exactly right. Like this is the future, right? We have both. You got to have the high level planning implemented in some kind of symbolic way, and the low level thing implemented in some neural network black box way. So we need both of them.
I see. Yeah, maybe uh yeah, we need to move to the next part. So I have just one last question
Yeah.
About the simulator. So if we can assume that we have simulator, then the simulator can understand the code, and many of the cases we can find some code snippets about the simulator, the environment. And MindDojo Eureka both somehow exploit that aspect. So, but the real world
Mhm.
cannot execute the code, and we have this
Mhm.
issue, which I sometimes call the curse of a simulator. So
Mhm.
either we need to build the if it is a totally new environment, we need to build the simulator of the environment. If it is doable, then all the techniques we have developed, or like what you have done here, can be easily applied. So, um, yeah, going beyond the simulated environment, what would be
Mhm.
the solution we
Mhm.
can take for eventually if our target is real physical world?
Mhm. I think real physical world is like a whole next level of difficulty because there are like many things to overcome here. So one way is sim to real.
Mhm.
And I think NVIDIA is very big on simulation. So sim to real is there are also many kind of proven success of sim to real where you do like enough domain randomization in sim so that the real world becomes like a subset of the simulation distribution. And another interesting way is to do real to sim to real. So you kind of transport the real world to sim, you instantiate it in sim and train it and then export back to the real world. And this part is kind of like inverse graphics, basically. So kind of computer vision and also like neurosymbolic can be used in some ways because simulation is code, right? Like can we kind of generate some code that drives the simulation to be like real world and export that back. So real to sim to real is like another way. And directly doing things in the real world, I think is gonna be very difficult. So one way is to just scale up on the kind of the human demonstration data. And I think that's what Google Brain Robotics does. So RT1 and RT2 rely on a lot of human demonstration data. And they have like maybe dozens of bots and dozens of human operators collecting that data for like half a year. It's like extremely time consuming and difficult. And I also don't really see like a better way to do if you stick to a real one, not use simulation. You got to collect data in some ways. So it's quite tedious. But I do think like some kind of data or like human teleoperated data in real world would be useful. And here is one way to use that more effectively instead of collecting like everything manually. So about like 2 months ago, my team and I co-authored a paper called MimicGen. And what MimicGen does is we ask humans to collect demonstration. And then we instantiate that demonstration in simulation, and then we do basically data augmentation. But the data augmentation is semantic, where we swap out the object, we perturb the trajectory of the human hand, of the human teleoperation in some ways to generate completely new data, new like demonstration trajectories in the simulation. So for every kind of human collected trajectory, we can generate 100 very different trajectories based on that trajectory, doing editing in the simulator. So in this way, we multiply the human data by 100x with the help of the simulator. And it's very much real to sim and then back to real. So we train things over there and we export it back to the real world. And we found that it actually improves the real robot performance by a lot. and I encourage students here to check out MimicGen. I can leave the link in the chat.
Yeah, yeah.
So that is one way to use it. But again, I don't really know what a robot foundation model will look like. It's probably some multimodal foundation model, but how to train it, where the data comes from, how big of a part simulation will play. I think these are like there's no consensus on these. And my personal take is I am very big on simulation. I think simulation can play a critical part in it, but plenty of scholars disagree. So we'll just see how it plays out.
Yeah. Yeah, actually, I'm the part agreeing the importance of simulator. Yeah, that's the way we can like maximally utilize the power of machine learning, like a data driven, because where we can infinitely many data can be generated, and then don't need to be limited by the real time constraint. So so one thing I see is like the other research community, like video synthesis, like using nerve. So that area is like moving very fast. So I was even imagining like we have iPhone and there we have like a depth camera, all the cameras, and then it can take a picture of the scene, and then from there somehow it generates the object, which is becoming the object in the simulator. So like a real to sim kind of real time. I mean, making the simulator very fast just by taking pictures. I think the field is going toward that direction, but yeah, then the simulator will be very useful. So, what do you think about this?
I completely agree. I think also like text to 3D and the one you mentioned, kind of basically scanning the world in real time, and also like AR and VR are becoming much better. And like for example, like Oculus Quest has a lot of great computer vision models built in, and like these models are becoming really good at understanding the 3D spatial of the world. So yeah, that's why I brought up real to sim to real. I think this is a very powerful paradigm, and also combined with some amount of real data, I think it's gonna kind of this paradigm will take it quite far.
I see. Yeah. Right. Cool. Yeah. I think we can do some questions more like feed it to this AGI seminar. So I prepared some questions. So
Awesome.
Let's do it. One question is about like what it means AGI itself, because I see in the internet there are a lot of discussions and arguments about like a risk of AGI or whether it will be like removing human jobs or not. So I found all behind all this discussion, I feel like every researcher or professor, they have their own definition of AGI. So there's really, I don't see very good consensus in the field. So to talk about anything about AGI, I think it would be good first define your version of AGI. When are you going to be happy or could say, okay, finally we have AGI?
That is a great question. I get asked that question all the time. And I think since we were already talking about robotics, I would say my definition of AGI will be anchored a bit towards robotics. So I'm calling this the physical Turing test, right? So I think the software Turing, the chatbot Turing test, GPTs have passed that long ago. You can pretend to be a human and we wouldn't even notice for a very long time. So I think that part has passed. But the physical Turing test is so much harder. So the statement is, can we have like fully embodied robots that look completely like humans and behave and talk like humans and do actions like humans? And you live with that robot for a couple of days and you can't tell the difference between that robot and humans. So basically some scenes from the TV series Westworld, if the students here saw that show. So can we have something like Westworld? And when that happens, I would say AGI has been achieved because embodiment is key to intelligence. I don't believe a chatbot will be AGI. I think having this full embodied experiences and really grounding these concepts and also interaction with humans in this naturalistic way will be an essential feature of AGI.
So it's related questions. Yeah, that's very interesting perspective. So do you think, because some people believe that LLM, which doesn't have embodiment, is already
Mhm.
very core part of AGI. Do you think without embodiment, the current LLM has fundamentally limited and having body, the LLM can finally be
Yeah,
capable to be more. So yeah, can you say something about this limitations of LLM in relation to embodiment?
absolutely. Um, I think there are kind of two angles to this question. Like one
Mm,
is a more of like a philosophical angle, and the other is more like
mm,
operational angle. So
mm,
from the philosophical point of view, right? I think embodiment is the best way, maybe not the only way, but the best way to learn world models,
mm,
causality and decision making. And what does a world model mean, right? World model means if you take an action, you can kind of simulate in your head. It's a mental simulation. You can play out in your head what could be the possible outcomes. So it's a very kind of strong instantiation of like causal understanding of the world, of intuitive physics, of kind of these like reasoning rules. And also philosophically, like humans, right? Human kids, babies, they don't learn by reading 10,000 million articles on Wikipedia. They don't do that, right?
mm,
Like when we were born as babies, we start learning about the world by experimenting with it, by interacting with it, poking things, putting things in our mouths, feeling things around, and hearing and seeing everything, right? Like that's how babies learn. They do experiments. So there's the saying that babies are scientists in the crib. And I love this saying. I think that is
mm,
fundamental to learning and understanding world models and truly internalizing like causality and decision making. So philosophically, I feel that is kind of what LMs are missing. And it's really hard to bridge the
mm,
gap without some form of embodiment. It doesn't have to be in the physical world. It can be embodied in simulation,
mm,
but it's got to
mm.
at least have decision making and rich feedback in the loop. So that's philosophical. And the second point is more operational. So we are facing a very serious problem and a very kind of immediate problem is that LLMs are running out of high quality tokens to train. I
Mm,
think some of the top LLM companies they have already scraped most of the internet for high quality tokens. The rest are maybe low
mm,
quality, but there's just so
mm,
much high quality tokens you can scrape.
mm,
And then there is diminishing returns now because of the lack of high quality tokens. The supply is
mm,
dwindling. So the
mm.
question is, where does the next trillion high quality tokens come from? And my hypothesis is that it comes from embodiment, maybe in simulation. Because in simulation, you can generate infinite data, right? You generate that the agent generates the next trillion tokens to train itself on. I think that is the way to really solve the data problem, right? This is a very operational and a very realistic difficulty. Where does the data come from? And
Mm,
the other good thing is because the data tokens are now self-generated, it can be generated according to the internal uncertainty model, basically exploration, right? You explore things that you're most uncertain about, and you don't need to train on the tokens that you are already extremely familiar with. And only with an active agent can you do this kind of active data collection, right? There's a whole field of how to do exploration in kind of an informational theoretic way. And I think that is the path to unlock more data and high quality data and data that can actually directly, in the fastest way, improve the agent's intelligence.
yeah, fantastic. Great. That's very insightful, really thought-provoking. And yeah, so now I think for the remaining time, like beyond research and just like a technology, I think we could talk a little bit about like a different topic. So many people would also be
Sure.
interested in. So you are very active, like AI and influencer in Twitter. So and I actually
Yeah.
found that I try to count your followers. It's like 153K like followers. So I think it's one of the most like yeah largest number in AI field. So what motivates you to do? Well, what does it mean doing Twitter to you as being a research top research scientist? What does it mean to you to tweeting?
Yeah, that's a great question. Um, so I see Twitter as a place to open source my ideas, basically. To
Oh,
get
mhm,
conversations going with people that I wouldn't otherwise have access to. And that is kind of one part of it. I feel, Twitter kind of broadens my horizon and also exposure to many and not just researchers, right? But many kind of many people from different walks of life. There are like artists kind of following me and having very interesting conversations with me. There are designers and hardware engineers, like many people, right? It's a very interesting experience. And second, I see this as a kind of community service, basically
mhm,
giving back to the community by helping increase the signal to noise ratio. Especially earlier this year, right? Like ChatGPT, when ChatGPT first came out and then GPT-4 hits, kind of the world exploded on Twitter and on social media, right? There are so much hype, and many of them are just noise. And if you go on Twitter these days, you will see a lot of posts like 10 GPTs that are insane that blow your mind, 10 different prompting tricks that you should not
mhm,
miss, 10 ways to use ChatGPT to make money. It's just like so low quality and it's a waste of everybody's time.
mhm,
So I see this as a community service because the people who are posting 10 GPTs that are insane, they are not AI researchers. They have no idea about the
mhm,
field. They just come here because of the hype, because of the gold rush. But Sunjin, right, you and myself, we were here for like so many years, and we saw the field grow. We understand
mhm,
what are the real problems, and we can sift out, the real problems from the hype, and
mhm,
give the community and all those sometimes even decision makers who are not familiar with AI, but they need
mhm,
balanced information. They need accurate
mhm,
expert
mhm.
input, and that's what I feel I could be most useful to.
Yeah, and that's fantastic. Really, yeah, every time I see your post and what I see is it's not just like delivering just the fact, the information. You always have your own insight there, and that insight is from the high quality top researchers' insights, not from someone like non-research. I mean, from people who are not actively doing research. So I myself find it very, very helpful. And also, as you said, like it's very impressive to say you're open sourcing your ideas. So I found many of your insights there is very valuable insight. Someone could even start a research project with that insight, but you don't try to hide it. You share the idea, and so you don't have any fear of sharing your idea, but you are more like you feel that you gain more by doing that, right?
Exactly, exactly. I think that's the power of open source
Mm,
in general, right? Open sourcing software, open sourcing
mm,
model, open sourcing idea. After you open source, you seed more ideas for the community, and then the community grows
mm,
exponentially, right? Like sometimes I
mm,
read people's replies and I'm like, huh, that's an interesting idea I didn't think of, right? I get
mm,
ideas from the community as well. But if you don't
mm,
sow the seeds first, you will never get a fruit back. And that's how
mm.
I see it.
I see. So regarding that, can you give some advice to students? Mostly, so I was the same when there are a lot of graduate students here, but they are mostly focusing on writing paper, but there's
Mhm.
maybe not much room to think about like contributing to the community or becoming a voice in the field. But that is also a very important part of in the path of going
Mhm.
to be a good researcher. So maybe can you say some advice about as a graduate student what they can start or how it is important to
Mhm.
be a good like a becoming contributor or leader of the community and so on.
Absolutely. Yes. So here's what I think. I feel that, what separates a bad researcher from a good one is the ability to solve a problem quickly. But what separates a good researcher from a truly phenomenal researcher is actually the ability to identify problems worth solving. So what I'm saying is sometimes asking the right question is way more important than answering it. And that's what we call research taste. So Songjin, I have like when last time we chatted, I have a lot of admiration for you because over my PhD years, I've been following your works and I saw great research taste, right? I get inspired by your works. And I think that is the hardest part. Yeah, I'm not flattering. This is true, and that is the hardest part, right? That is what makes a phenomenal researcher. And I see the audience here at Zoom. I see a bunch of the smartest students, right? You're at KAIST, you're attending Songjin's seminar. That means all of you are extremely intelligent and hardworking, and I have no doubt about it, right? But what matters is where you apply this energy to. All of you are extremely smart, but where do you apply that to? And I think research taste is something that cannot be taught. Coding can be taught. You just go ahead and take a Python class. You learn coding. Machine learning can be taught. Research taste cannot. It must be acquired kind of intrinsically, through trial and error, and lots of self-reflection. Just read a lot, talk to a lot of people, and go on social media, try to engage in like meaningful conversations, and do projects, right? Get your hands dirty, do projects and fail again, and fail again once more. And then you get what are the problems we're solving? What are the questions that actually lead to meaningful and inspiring answers? And I am not a fast learner. It took me 5 years of the entire PhD to finally converge of some of the ideas that I have today, right? There is no shortcut at all. So that is my advice to all the students here.
Yeah, cool. Yeah, cool. Great. Yeah, also related to that, I sometimes tell to my students, as a junior student, what's important to them, like in the beginning, is just publishing, just accepted their paper. But what I see from your portfolio of research, you're like targeting a moonshot project. So like don't try to be like just writing papers. Someone else can do that, but targeting like this kind of moonshot grand challenge. But there's also at the same time to students there's some risk or they could be a little bit afraid of can I do this? So do you have some advice or how we could encourage a student to like try to tackle like a big challenge?
Yes, I think there is a kind of a fine balance between, one is like a huge ambition, a moonshot, and also, at the same time, stay grounded. So I think this balance is very delicate, and it's also more of case by case and dependent on kind of where are you in your career. Like, let's say you're a beginner to research, then for sure you should stay grounded. Just get your hands dirty. Even re-implementing, reproducing some of the prior works would be a great exercise to get started, to get a kind of a sense of how to do research, how to implement, do ablation studies. You got to have all the basic stuff, right? You need to train the basic skills and be like a rigorous and systematic researcher first. And then if you feel comfortable now, kind of basically I give you any paper, you think about it, you know what are the tools you need to reproduce it, you know how to reason about the strengths and weaknesses of the paper if you think you're ready. And then we're talking about setting longer term goals. And for the longer term goals, right, we need to set it to be ambitious, but also realistic, where you can break it down to maybe like a 3-year plan, right? Don't plan like anywhere longer than 3 years. I think it's just too difficult and too unpredictable. And anything beyond 3 years is more like, dinner table talk. I'm just having this wild dream. But to stay grounded, let's just plan for 3 years, right? This is let's say the one big goal is to solve Minecraft. Now, what do we need if you're given 3 years? And these are maybe the milestones that we need to hit to solve Minecraft. And each milestone builds on top of the previous one. And you're also very clear that what is the limitation of each work, what problems does it solve, what does it still lack, and you measure the distance from that goal and you reevaluate. Basically like model-based planning, right? You roll out the model and then you plan a little bit, you take a step and you replan, right? Given the current new situation and new information. So I think this is a very much an iterative process and it's very case by case. Every researcher I know has a different cadence. They have a different kind of agenda that they feel comfortable. And I don't want to prescribe any kind of fixed plans, but I think this kind of general purpose framework is how I would use to approach research.
I see. Yeah, great. Yeah, great answer and very insightful. Maybe this could be the last question. So I'm being in academia and you're in industry. So wherever we are, this AI field is moving so fast and things are changing so quickly. So I also see many of the students who are wondering in their career path, should I go to industry or would it be better to be in academia? So, or even how like this academia industry can cooperate for the advance of the whole community. So can you give some advice to students about like your experience in being in industry researcher and also, but you are in like Stanford University for your PhD, so you're also well familiar with the academic setting. So some advice about the career in that sense.
Yeah, I think that is a great question. And these days it's like the whole field is extremely fast moving. And I feel that in terms of kind of the largest models, the biggest foundation models, for sure industry is leading because they have the most resources, right? Like that's kind of by design, like they have all the resources and huge teams, so they can build extraordinarily big models. But I feel that for many of the kind of the research problems, especially on the most cutting edge of some of the things like embodied agents and robotics, I think academia still has a huge amount of great ideas, and industry does not necessarily like kind of big companies are not necessarily able to try out all of these ideas because they are more kind of profit driven. They have an agenda they need to execute. They cannot kind of do wild ideas. But you know, like academia can. You can think freely. You don't have to deliver a product, and that gives you a lot of leeway into trying out crazy things. Right. So I still see like, you know, there will be pros and cons on each side. And then the other trend I see is an increasingly closer partnership between academia and industry to kind of combine the strengths of both. Right. Academia is like more kind of free form thinking and open-ended, right? We're talking about open-ended simulation a lot. Academia, I think, is more open-ended. And industry has the resources and the kind of engineering firepower. And we see increasing partnerships. You know, a lot of students go to industries for internships, and they do some of their best works in collaboration with their university professors, and also, you know, the resources and the mentors and industry. So I definitely recommend that. And for sure, I am a bit biased. You know, NVIDIA is a great place. So you saw my contact. You know, you know who to find. I can also share a bit like why I chose NVIDIA after Stanford, after graduating from Stanford. So I always wanted to do agents, and at the end of my PhD, it became very clear to me that embodied agent is kind of the next holy grail of AI that we need to capture. It became very clear. And NVIDIA, I saw two unique strengths. One is for sure, you know, AI part, right? LLMs and AI and foundation models. It was already clear in 2021. And the second part is simulation. And actually, NVIDIA, before it was an AI company, it started as a graphics company, right? A gaming company supporting simulations. So the history of simulation and gaming is actually longer than the history of AI within the company. And therefore, NVIDIA actually built, you know, extraordinary kind of technical abilities to do like hyper realistic GPU accelerated simulations that are like 3 orders of magnitude faster than real time. And I see embodied agents to require both foundation models and simulation. And NVIDIA is one of the very few companies that sit at the intersection where it's good at both. So that is why I chose the company. But things will be different for the students here in the audience, right? If you prefer computer vision or like music generation or like different problems, that different companies have different strengths. So you want to choose your partners also very, very wisely, right? Which company you're going to intern at, which mentors you will partner with. So I would recommend studying kind of different strengths and weaknesses and see which company is complementary to a strength.
Yes, thank you, Jim. That will be really helpful to students. Actually, yeah, I see many students having similar problem, like where to go. But I think sharing your experience will be very invaluable to many students. Yeah, so that's it we prepared today, and actually this is our inaugural seminar session, the beginning of this AGI seminar series at KAIST. I can't think of any better speaker than Jim Yu, so it was just really fantastic, and I guess many of the students also felt really they really got really invaluable lessons through this talk. So I really thank you again. And unfortunately, this is fully online, so we can not give you like a big applause, like large enough. But I think everyone here is like giving you a big applause. So thank you very much, and let's keep in touch later again.
Thank you so much, Sungjin. It's my honor to be the inaugural speaker. I can feel the energy, from Zoom flowing into me.
Yeah.
So next time, yeah, we'll love to visit KAIST and Korea in person. So looking forward to that.
Yeah, looking forward to that. Yeah, thank you, Jim. See you again.
Awesome. See you all soon. Bye.
Yeah, and thank you, everyone. Bye. Have a good weekend.
Thanks, everyone. Yeah, bye.